system. That's what's happening in our system. So last 2 days have been pathetic for our internet. So now we have started, Professor. I mean, you can begin. We welcome all the participants and Professor Bengt.
But you haven't started the recording yet, or?
Pardon?
You haven't started the recording yet, or?
Yes. Yes, please. Thank you. Thank you.
Okay, so welcome to this seminar or lecture today. And yeah, maybe I should have gone through some repetition first before I start. But I think I take that later. Now I have them. Let's see here.
Could you go through the revised schedule that I have shared with you?
Yes, we okay. Should we take that now, you mean, or?
As you say, I mean, if you think that
I would prefer to take this in the afternoon, so I can, because I haven't looked in detail to it, and we can discuss a bit more. Yeah.
Okay, fine.
Thank you. Okay, so as you noted yesterday, it worked better when I didn't went into the full presentation view, so I stick to this view of the presentation. Okay, so for today I will go back to and develop more on the alternative modeling procedure, namely Petrinets, and also to show how things can be related. So in the end, I will propose, or during this presentation, I will propose a model framework, which actually I mentioned already in the introductory lecture, which can be considered as a unification of more or less all the available modeling framework that are in hand. And I mean, if you compare with, for instance, modeling of continuous time systems or a continuous state system with state space model and Laplace transform and Z transform and so on, you could say that for those kind of continuous systems like temperature, pressure, velocity, dynamics, then their differential equation is the main framework, and of course it's very well established and well known. And you could say that the transfer function and the transform plane, so to say, with Laplace and Z transform is then the alternative, but it's somewhat limited only to, for instance, linear systems. But for the type of systems we are working with in this course, discrete systems, discrete space, it could still be continuous time. I used to call it discrete event systems based on my background, but you can also say that it's kind of finite state systems. We could say that we have still two main modeling framework, but there are many dialects, and that is simply because there is this part of the science or applications is more a new topic which has not established something as common as differential equations. You could say that basic automata and finite state machines is really the basic platform. Everything can be described more or less in that way, and today we will also extend and show how we can extend with time and also include continuous time dynamics into the system. But then there is another big area and a big way to describe this type of systems, and it's called Petrinets. And I've just indicated very briefly how that works. So now I will go through that in more detail. And as I think I mentioned already in the introductory lecture, this model, there is actually an interesting discussion and a small fight between those communities that say that, okay, well, Petrinets, they are much better than finite state automata, because finite state automata are restricted in the sense that, okay, I mean, if you have a system with, it's enough with saying, say, 1,000 states. I mean, to write an automaton with 1,000 states, it's something you cannot at least make on paper, and even on the computer, it just gives you a total mess. While then a graphical model for that in a Petrinet could be quite readable, and I mean, it's easy to construct examples where an automaton gives you a totally unreadable model, while the Petrinet is still very readable and understandable. On the other hand, then the so to say automata community says that, well, but then you have missed something fundamental, namely that we have the synchronous composition. We had the opportunity to model systems with small automata that are synchronized with each other. And then you have this modular description. And actually with that concept, you could say that in some sense, automata that are connected to each other are more or less equally readable. Even more if we then add variables, logical variables, or say integer variables to the automata, and then we get what we call extended finite automata or extended finite state machines. In our group, we established the word EFA some 10 years ago, meaning extended finite automata, yes. And these EFAs are actually very interesting because you can model systems in a more powerful way. But if you look at that structure, you will also find that, well, okay, now you introduce variables to represent your system together with events. Why not take that completely? So we say that all things are represented by variables. And then you could say that it's perfect for implementations, but not so nice for visualization. And then to combine these variables, logical or integer variables, with either automata or with Petrinets is what I think is the most powerful model. And in my case, since I think that there is something good with Petrinets, my own proposal is to use Petrinets with what I call shared variables. And that is, I wouldn't say it's my own invention totally, but I'm one of the few who strongly proposed this, and I have written some papers on this. So with that background, I will start now with Petrinets. And you could say that also that, I mean, there is a big community or a number of communities, I would say, that are using Petrinet. So having some knowledge about that is definitely of interest. And there is, if you go for PLCs, which at least some of you have experience on, then you could say that there are languages in the PLC which you can program in. One is sequential function chart, SFC, and that is inspired by a French standard called GraphSet. And GraphSet is, in its turn, a version of Petrinet. So Petrinet has really influenced also the industrial area related to control of production systems, etc., based on Petrinets. Okay, how do we find a Petrinet and how does that look like? I go back to this buffer system I introduced for the first time. And here you have input events, meaning that a part arrives to the buffer, and an output event B, meaning that you take away a part from the buffer. And if you have a buffer with 4 places, then that could be described by this automaton. And alternatively, we can also describe this by a Petrinet, and then the initial state is here, these 4 tokens in the place. A Petrinet has places and transitions. So it's a bit confusing with this example because I'm talking about the number of places in the buffer, but also more generically about places in the Petrinet, which could be a bit confusing. We could also talk about the number of elements in the buffer and the free space maybe in the buffer to avoid using the notion place there. So the number of empty capacity of the buffer, it's in this case 4. And now there is no element at all in the buffer. It's empty. It's empty, but it has a capacity of 4. We can say these 2 places represent them. Then the first transition must be an A event, meaning that a part arrives to this buffer. And here you see that I have both the event label and I also write here T1. And we talk more explicitly about transitions also in Petrinet. So that means that you have a token here moving from this place P2 when the transition T1 happens, and that happens when the event A is executed. Or when the event A is fired, we also say in the Petrinet literature. Then a token is moved to this place, P1, where we have the number of tokens represent the number of elements in the buffer. And then you can continue with that for 4 times. And then there is no, then the buffer is full. You cannot make any more A events, but then you can take away elements and bring them back to place P2. Okay, so this text here describes exactly the dynamics, what happens when you move the tokens back and forth. Now we can look at the number of tokens in the 2 places, and then we talk about MI as the number of tokens in place PI. So M1 and M2. M1 is the number of tokens in the place P1 that represents how many parts that are in the system. So when transition T1 happens, you increase from 0 to 1, and then 1 more T1 to 2, 1 more T1 to 3. And then T2 means that you take an element away and then go up with another T1. And you see that I have not gone up to the upper limit to 4. This value is 3, 2, 1, 0. And then there is an image of this where you could say that the M2 the value M2 is just 4 minus M1. So that means that when M1 increases, M2 is decreasing. So here you can say M2 is the number of empty, the number of empty places in the buffer. In this way, you can say that these diagrams here, they corresponds to what you can see in state space system, where you have a trajectory for, say, the first state variable, in this case M1, and the second state variable M2, if you have some knowledge about dynamic systems and state space models. So this is something that connects very well to state space models. And you could say that these two variable M1 and M2, they could be considered as state variables. So the vector M1, M2 represents the state of this system. Then we come to the mathematical definition of a Petrinet. It's what we call a net. So that's why we use the notion N or the letter N. Now, instead of having a set of states, a set of events, etc., we have a set of places and a set of transitions. And now I take one example here, a little bit different to the one I showed you before. It's actually very much related to the standard example I have used also before, when I take one A event, and then I can make either a B or a C event to get back. So you could say that that example is more or less the running example through the whole course. The very basic example. So in this case now we have four places, P1, P2, P3, and P4. And we have three transitions, T1, T2, and T3. So in that sense, the set P includes the element P1, P2, P3, P4, and the set T includes the elements T1, T2, T3. And then the magic question is about A plus and A minus, how they works. And I will explain that on the next slide. But it's interesting that if you look at this Petrinet, it can also actually be modeled by two automata, A1 and A2. A1 making an A and then B, and the other one taking an A and a C. And here you note that A is a shared event. So it is the fact that when you synchronize A1 and A2, you get a model which is exactly the same as this one. And we will see that also more explicitly later on. So A1 synchronized with A2 models the same behavior as the Petrinet. And then I come with this comment again, which I said before, that a Petrinet can represent a number of automata that are synchronized. But if you accept a modular procedure in your modeling, then this Petrinet can also be described as a number of individual automata that are synchronized. So there is a clear connection. And to make it even more complex, we can say that even Petrinets can be synchronized with each other. So there is a kind of flexibility here. But you could say that in the literature, the normal assumption is that you only have one Petrinet, while you could have a number of automata. Okay, so P is a set of places, T is a set of transitions. Generally, we assume that we have n places and m T transitions. Okay, A plus, that is a matrix now, defining the number of tokens moved to the output places for a transition. So what we need to do with these matrices A plus and A minus is just to tell how these transitions are defined and how they are connected between the places and the transitions. And then the A plus is defining how many tokens that are moved from to an output place for a transition. Okay, what is an output place? Here you have a transition with two output places, P3 and P4. And then, of course, P1 and P2 are then called the input places. So when this transition T2 happens, these two tokens, they are taken away from the input places and moved to the output places. And that is that we should now represent by these matrices A plus and A minus. So generally, we can also have a number, we can take a number of, or we can add a number of tokens to an output place. So that means that we can actually add a weight on the output transition from this transition T1. So instead of, we could write 3 arrows here, which means that you will add 3 tokens to this place when the transition T1 happens. But that could also be described in this way with a slash on the arrow or on the edge and the number 3. So when T1 is fired, 3 tokens are added to the output place. But in our example, the A plus matrix is, and then you have the places on the different rows here, and the columns represent the transitions. So P1 was an input place. Sorry, let's see here. Okay. T1 was is this transition. I was thinking about T2, that made me confused. Okay, T1 is the first transition on the left side here. And by that you see that when that T1 is fired, you will add 1 token in P1. And when T2 happens, you will add 1 token to P3 and P4. And when T3 happens, you will add 1 token to P2. Let's see if that is correct. Yes. Okay. When T1 happens, the place P1 will be added 1 token. So that's why we have a 1 in the first column and the first row corresponding to the first place. In the second transition, we add 1 token to the lower places P3 and P4. And in the third transitions, we add 1 token to the place P2, the right upper place here. So then we have defined the output places of the different transitions. And now I will define the input places by the A- matrix. So A- defines the number of tokens moving away from the input places. And maybe you remember now that P1 and P2 were the upper places in the model, and when the transition T2, the middle transition, happens, then we need to take one token away from P1 and one from P2 to make that transition possible. And that's why we put 1, 1 here in the T2 transition. While the first transition, the left one, adds one, to be able to perform T1, you must take one token from P3. And for T3, we must take one token from P4. So for T1, we take one from P3, and T3, we take one token from P4. And once again, the middle transition takes one from P1 and one from P2. So now we have defined the two matrices that describe what is happening, what we add to places, and that's A+, and what we take away from places, that's A-. Now the vector, including the number of tokens in each place, is called the marking vector. So M is the marking vector, including the elements M1, M2, M3, M4. And normally we work with column vectors as the standard. So that means that we need a lot of transpose here to save space to write them out. So Mi is the number of tokens in place Pi. Then to define the Petrinet completely, we also need to tell the initial state or the initial markings. And that is that you have one token in P1 and another in P2. So the initial marking in this example is 1, 1, 0, 0. Now I would like to give you an equation telling you how the dynamics is of this system, how the tokens are moving around, and represent that in an equation format. And to do that, I need two small pieces of non-usual mathematics, we can say. And that I call Sj, which means that in position j in this vector, you have an element 1, the rest is 0. So that's the selection vector. And actually, I will use that to select a desired transition. So for instance, if I'm interested in to say something about the first transition, then the first element, S1, is used. If I want to select the second transition, then I have, in this case, I will have the non-zero, the one element is in the second position. Then there is also an ordering between vectors, which is not totally standard notation. But if you say that x is greater or equal y, by that I mean that all elements in x are greater than corresponding elements in y. So every element in x must be greater or equal every element in y. If I have those notions, I will be able to talk about some important properties here. And the first thing is that a transition the transition T2 is possible, or it's fireable, or it's admissible when the token vector is greater or equal to A minus multiplied by the selection vector S2. And S2 is then is selected because I'm interested in transition T2. So if this marking vector is greater or equal, okay, multiply a 0, 1, 2, it means that you select the second column, and then M must be greater or equal 1, 1, 0, 0. So you could also simply say that, well, if there are at least as many tokens as corresponding column vector in A minus, then the transition T is possible. So for instance, to make a T1, you must have at least one token in place P3, and the second transition, at least one token in P1 and one in P2. There could be more tokens, but so this is the minimal number of tokens that are required to make a transition fireable. So that means that M1 must be greater or equal 1, at least one token in the first and second place, and in the third and fourth you don't need. Now I get some messages. You shared screen can. Your share screen can be seen only by the host. Oh. Meeting in focus, only host can see your video. Okay, does this mean that you have a problem to see my presentation, or?
Yes, sir. Actually, ma'am has become again host. So I'll call her and ask her to make you host once again, sir.
So you mean that you haven't seen anything, or?
No, sir. Nothing is visible from your side, even not your video as well as your slides, whatever you were sharing. So can you, sir, again share all these?
Okay. So, but it's amazing that no one has said anything. But was this that something that came up now, or? Oh yeah, okay.
Just now, sir. Just now.
Oh yeah. Okay.
Just now, sir. Just
yeah. Okay. Meeting in focus mode. Only host can see you. Okay. But I clicked this now, and okay, we are still recording. Fine. Let me just first see. I have got a question in the chat. Oh yeah, okay, we cannot see. So then let's try to share again. Host disabled.
Yeah, sir. I'm talking to Ojha ma'am. She will be giving you the rights to share. So, sir, okay. I'm very sorry. It will take hardly half of a minute. So.
Yeah. Okay. Hej Benjamin, jag är upptagen. Du får prata med mamma. Okej. Ja, jag sitter i föreläsning till Indien. Okay. Things are not totally stable.
We are very sorry, sir. We are.
Yeah. I mean, it's no problem for me. It's good I get some rest.
Yeah, sir. Yeah.
So maybe I could ask you then, because we can at least talk to each other. Is it any one of you who have seen these Petrinets before? Yes. No one?
I have seen. I have not much, but the basics I know.
Okay. In which kind of applications have you seen that, or is it just a mathematical tool for you, or?
No, sir. I
Ah, you are. Yeah, yeah, of course, then you are. Oh, it's interesting. Have you looked at any specific applications or?
Not as such. I mostly use finite state automata.
Yeah.
Yes,
Okay.
now you're, sir. I'm very sorry to interrupt. So,
Yeah.
sir, you are once again, your videos, we can see you. Now you
Okay.
can share, sir. Yeah.
Yeah. Okay. Let's go on.
Yeah, so cool. Now it's fine, sir. Yeah.
Great. Great. Thanks a lot. Thanks a lot. Yeah, I mean, it would be interesting to have some short discussion later on to see also what kind of backgrounds you have if you have worked on this field before. But let's come back to that. Now we go on with the presentation here, and we had came to the conclusion that there is a specific condition that must be fulfilled to be able to perform a transition, and that was that our marking vector must be greater or equal to A minus multiplied by the selection vector corresponding to the actual transition. So if a transition is fireable, if it's admissible, possible, then you will also have an update of the marking vector. And that is, of course, quite naturally related to these A plus and A minus matrices, is actually A plus minus A minus, and then multiplied by the selection vector for the vector you are interested in. So then you take the current value of your marking vector plus this A plus minus A minus multiplied by Sj, and then you get the updated marking vector M prime. So this means that this can be considered as then as a state equation. And this transition, this update is possible when then M is greater or equal A minus multiplied by Sj. And when transition Tj is fired, you will get this update. So you could say that this equation is a way to mathematically or also algorithmically simulate the system. So when the transition is possible, you can see what happens when you perform that transition by executing this equation. And then you can play around with this and actually generate all the possible marking vectors. And since I said that all these marking vectors represent the state of the system, what you will get out of that is actually an automaton, which is also in the Petrinet literature called the reachability graph. Let's see in more detail now, what was A plus minus A minus? Well, this was A plus, this was A minus, and I just see here that you get this result. And we could at least check this for, say, one transition. I will just take a look at, no, okay. Let's say, for instance, that we have this initial transition, and then we make the transition T2. That means that we will add to M1, we will add to M0, we will add this vector, the second column vector in A plus minus A minus. And that means exactly that we will take away these two 1, 1 here, since we have -1, -1, and we will get the M prime will then get 1, 1, as you see here. So this is M1. And then based on this vector, if you take the marking vector, if you then take the transition T1, the result will be that okay, you add this vector to this existing vector, and then you will specifically add one element in the first position of the vector. And you will take away that element, the third, and the fourth will stay there. So then that's why you get 1, 0, 0, 1. And note that all these vectors are formally column vectors, and that's why when I write them as row vectors, I have to introduce the transpose all the way. So here we started with the initial vector. We had this transition, and then we have either T1 or T3, and then we get back to the initial state again. And this is called the reachability graph, because that is actually a way to describe all the reachable states of this system. So by generating the update of this state equation, you get this reachability graph. The corresponding automaton, which I indicated very early, is A1 synchronized A2, and that is obtained by also letting A occur in both A1 and A2. And the synchronous composition A1 synchronized A2 is actually this model. And that means that it's not exactly the same running model I have used before. So what this says is that, okay, first I make an A, and then I can make a B or a C, but I have to make both B and C before I'm back in the initial state. So first A, then B followed by C, or C followed by B. So before I say anything more, we can say that Petrinets are specially developed for representing concurrency in a system. And in that way, it's very attractive and useful. So you could say that the concurrency of A1 and A2, the synchronous composition of A1 and A2 is nicely described by a Petrinet. The Petrinet is the following. Okay, I will mention more details about that now. So this model is exactly the same as the automaton A1 synchronized A2, the synchronous composition of these two models. That can also be generated as follows. So we translate then A1 and A2 to corresponding local Petrinets. So here is N1 corresponding to A1, and it's the same kind of behavior. The initial state is now one token in the first place, then a transition A. Note that we add always these additional horizontal lines on the transitions, depending on where they are, but orthogonal to the transition. You have a line, a short line. And the reason for that is that we need this because we could have a number of input places related to a specific transition. And that's why we need these extra graphical marks here to be able to join these two places to this transition, and also to add them from this transition to the output places. While you could say that this transition here it could be enough to have the automaton description, like just an arrow from this place to this place, and then the event label B. But to be conformed and equal for all transitions, every transition here has this additional line on every transition. So now we have described the synchronous composition of A1 and A2 by a Petrinet. And you could say that that is obtained simply by joining the shared transitions in the example, the transition with event A. So joining or just putting graphically on top of each other is the way we can do here. Join this transition with that transition and you get this. So that means that any synchronization of automata can actually be described as a Petrinet, which is a nice way to illustrate the behavior of modular automata. Yeah, this was something I had to add. I haven't written a specific slide on this. This is just a photo I took of the green board in my lecture room. It was just an illustration of the fact which has confused quite many of my students, and that is that the number of tokens is not constant generally. And this is an example illustrating this. In this case, we have two input places to this transition with event A, but we only have one output place. So that means if you start here with one token there and one token there in the other input place, after the transition A, we will only have one token. We started with two tokens, one in each input place, and after that we will only have one token in this place. But after this, now you have only one token here. When the transition B happens, you will add one token to that place and to that place. So then we have increased from one to, once again, two tokens. And then C and D can happen in any order. So that means you have a concurrency or independence of C and D. And after that, these, so to say, concurrent behaviors are synchronized by the E event. And so after C and D has happened, you have one token there, and it's first then you can execute the E event. And then in the end, you see a small token there. You have only one token again. So we started with two, we got one, we have two tokens here. For instance, that means that if D happens before C, you have one token there and one token down there. Two tokens, but after the event E, you have only one. Here it could also be interesting to look at the corresponding automaton. And here you can also see that, well, the automaton is equally readable. It's maybe only this independent concurrent behavior of C and D which blows up quite fast here. But first you have an A. The token there and token there is just represented by one state here in the automaton. Then an A happened, and after that a B, and then C and D in arbitrary order, either first C followed by D or D followed by C, and finally you have an E. Okay, let me just take a look here and see when we should take the break. Yeah, we can go on with 20 more minutes. So the Petrinets, this is an example. This is actually the example I have shown you before. Now I will show you also some other examples. And here is first an illustration of the fact that you could have more than one, you could require more than one token to perform a transition. In this case, I have two arrows from this input place, and that means that I require one one token for each of these arrows. So when this transition is performed, you move these two tokens from this place and you add them to the output place. But what happens actually is that in this case, you add 3 tokens. So you take away 2 tokens, but you add 3 tokens. So 2 arcs from input place and 3 arcs to the output place for N1. While for N2, we take away 4. It's necessary to have 4 tokens. In this case, we only have 1 token, so we cannot perform this transition, but we have to wait. Yeah, okay, the assumption is that this input place is connected to some other places. So there will be an input flow of tokens. And when there are 4 tokens in this input place, then you can perform the transition, and then you will add 5 tokens to this output place. A 4-weighted arc from input and 5-weighted arc to the output place. I would say it's not very common to have these weighted transitions, but since the theory and the model framework allows that, I also need to mention about it. Well, this is also a more tricky example illustrating the fact that you can also synchronize individual Petrinets. So in this case, I have first one Petrinet with a token here and an A event, and then another A event, and then you go back again. You could say that, well, this is for sure only an automaton, if you like. If you skip this transition markings and say that this is the initial state, then this is an automaton. So here the connection between an automaton and a Petrinet is very, the difference is very small. In this case, instead of making a repeated A, I make first an A and then B and then back again, and you can. So it's A, B, A, B, A, B, and here it's A all the time. If you synchronize these two, then the situation is that every transition up here with an A event must be synchronized or shared with a transition with an A transition in the second one. So then the question is, how can we arrange that? In fact, what you can do is to we look here at the 2 models, and then you see that the place P10 is this one. P now, okay, the inner one, sorry, the inner one is this model. So here you see the A and an A event, and it can go around like this. But the problem is that the other model, where you have places there and there, it can only make one A followed by a B event. So what happens then is that, okay, first you have one token there and there. Then you can make an A event. And then this model has to make a B, and that means that you have a token here, in that case, when the second transition, when the other one. Okay, sorry. We take this once again from the beginning. When they start they have tokens here, and then they can make an A event, and then you get one token there and one token there. Then the B event generates one token there, but then the A event can happen, and that requires this A event can happen, and then you have one token there and one token there, and then you move to this place, and then the B event needs to happen again, and then you can repeat this. So yes, it's a bit complicated, but it's just a way to show you that it is possible also to generate the synchronous composition between individual Petrinets. It's not very common, but it is possible. This is an example where B is a part of the, not a part of the alphabet of P1, but if it is a part of the alphabet of B1, then it's actually only possible to make one A event, because if the first Petrinet here cannot make any B, that means that if it's a shared event, if it's included in the alphabet of the first, since P1 cannot make B, P2 can also not make B. So that means that in that case, this is the restricted model. You can only make one A event, and then nothing more can happen. Now we come to something quite interesting, namely that you can also control or restrict the behavior of a Petrinet, and that is called then controlled Petronet, by adding arcs, additional arcs. So this was our original model, which has a corresponding language, first A, then B, C, or C, B, and then you repeat that. You loop around that, and then to get the complete language, you also take all prefixes of that. Now, if I would like to have this behavior ABC and not ACB, so I would always like to take B before C. So A, B, C, A, B, C. How can I get that? Well, that means that I need to put a restriction on the C transition, on the C event here. And that's simply that to be able to perform the C transition, I must have first made the B. And that can be modeled by adding these two arcs, which is actually does not change the number of tokens. It's just a restriction. To be able to make C, you must have a token here, which means that the token is moved to the transition, but immediately is left back to the place. So if there is a token here, you can perform the C. And then what will happen then is that first, these two systems or this Petrinet will take an A, and then B is free to execute. But C cannot be executed when you have the tokens down here, because it needs this token up there. So that means that you can execute B, and after that, now you can execute C, before it's possible to continue with an A, and then you repeat this procedure. So by adding additional arcs, you can restrict the behavior, and this is then called, we are talking about control of discrete event systems. So this is a way to implement control functions in Petrinets. Here is another interesting situation where actually we get a deadlock situation here. And there is a famous result on deadlocks saying that if you have shared resources, in this case, we have two loops here, you could say two tasks. This one would like to make A followed by B, this C followed by D, and then repeat. Now, the event A requires this resource, or it requires a token from this place. And that when that A transition happens, you take one token you take the token from that place, but also this one. And then you have a token here. Then to perform the B transition, you also need a token from this place. And these two places in the middle here could be considered as mutual resources that are, because this token is also required in this D transition, and this token is also required in the C transition. But let's see first what happens if we only execute this procedure or this task. First A happens, but when B happens, you leave the token back to the first resource. And when the B happens, it's only possible when there is a token here, but it immediately, when B happens, also leave the token back to that place. But still, to be able to perform the B transition, you must have a token here. So if we just look at this part of the system, it's no problem. You can execute A followed by B and go on like this. And in the same way, if you only execute first C, then you need the second resource, or the second token from the second place. And when you then fire the D event, you leave the token back to the second place, but you also require one token from this place. Once again, it works fine when only this sequence is going on, or this task. But what happens when you first take an A, then this token is not here anymore, it's there. And after that, not B, but C instead. Then we take this token, which is then moved to this place. And these tokens has also been removed. So after A and C has happened, we have one token there and one token there. But this means that B cannot happen, because B requires one token up there, and now there is no token in any of these two places. And D cannot happen either, because it requires a token up there. So both B is blocked because it requires the token from the second resource, and D is blocked because it requires a token from the first resource. So this is an example of when resources are required in opposite order. The left task needs the first resource first, and then the second resource, while the right task requires the resources in opposite order, namely the second resource first, and after that the first resource, before it has left the second resource back. Now, if you generate a corresponding reachability graph for this, and so to say, skip all the markings and just consider the states as circles, as nodes, then you get this automaton. And here we can easily see that, well, okay, you can make an A followed by B, and then you are back in the marked initial state. Or you can make a C followed by D, and you're also back in the marked state. But if you make first an A, this transition, and then a C, you get into this state. And from that, you can do nothing. in the same way as is you first take a C and then an A, the opposite order, but the first transitions in both tasks. Then you arrive into this deadlock state. So then the question is, can we avoid this by adding some additional control functions? And the answer is, of course, yes. We can also add arcs to this situation to avoid this deadlock. And well, it's maybe not so easy to see what we have done here. I should have required actually to have different colors on what I have added here is actually this two arrows and this two, and you could say that they are the added control arcs that are added. If you compare with this one, what we add here is that actually A can only be executed if there is it requires the first just for its own, but we also, for control purpose, also require that the other resource is free, because then we know that we need that resource later on when we should make the B. So we require that we make a test on when we take the A that, okay, the second resource is also required. And that is exactly what we're doing here. In the same way, when we take the C event, we require the second resource, but we also test at the same time that the first resource is available. And if that is the fact, then you can make a C. And if you have made the C, then the first transition in the A transition in the left task is not possible. So by these additional control arcs, we get the corresponding automaton is just that we skip these C and A events. We take away those transitions and we get either C followed by D or A followed by B. So to construct these additional arcs is, of course, not totally trivial, but sometimes it can be an efficient way to describe a control function. But I will later come up with something which I find quite much more useful and also readable to perform this kind of control functions, or to achieve this type of control functionality. So now I will just briefly repeat what I mentioned already on Tuesday afternoon. And that was these different types of behaviors. And first we have the straight sequences of two automata, A1 and A2, and the corresponding Petrinet is, you see, very, very similar. And also for the alternative sequences, the Petrinet is quite similar. On the other hand, we said that for concurrent sequences, when we have A1 synchronized A2, if there is no shared events and you have two transitions in each of the automaton A1 and A2, you get totally 3 multiplied by 3 states. You have 3 states here, and if you take that with another equal automaton, you get totally 9 states. You get also what we sometimes call the interleaving of these two. They have no shared events. Then if you add 2 more automata of the same type, you would get then 9 multiplied by 9, 81 states. But that can be represented by just adding 2 more of these Petrinet tasks. So A3 followed by B3, A4 followed by B4, and when they are done, you just add the final token down here. And as I also said last time, here we start with 2 tokens, and in the end we will also get 2 tokens down here. And if we have 4 sequences, in the end we will get 4 tokens as the final state of our system. So this is an example of a system where the number of tokens is constant, and actually that's quite common that the number of tokens are constant. Yeah, this example I didn't mention last time, but it is actually something we found quite interesting when I started with my first PhD student in this area, Martin Fabian. He's now professor and leading the automation group in my division. And here we have a combination of mutual exclusion, but also parallel sequences. So we say that, well, A1 and B1 should be performed, and A2 and B2 should be performed, as well as A3 and B3. And in principle, they could be performed in arbitrary order. That means, let's say that we could start with A2 followed by B2, and after that A3 followed by B3, and finally A1 followed by B1. But the order between all these 3 sequences, I don't care about. I call that arbitrary order. And to model that by an automaton, you see it's not a mess, but I mean, if you should add some more of these arbitrary orders, you should soon get something that is absolutely not possible to read. But here by the Petrinet, it's quite clear. The only thing you need to add to these sequences compared with this one is the mutual exclusion, meaning that, okay, when you have executed A1, then A2 and A3 cannot be executed. You have to wait until A1 takes this token and moves it to this place, and then we have wait until B1 has been executed, and after that, for instance, A3 can be executed because it requires also this token, and we call that procedure or that frame, that aspect of mutual exclusion, which models then an arbitrary order, but within the sequence of operations. I mean, here it could be it's only A1 and B1. It could also be a sequence from, say, A1, B1, C1, D1, E1, and then after that you have, so to say, performed the complete sequence, and then there could be a longer sequences also for these different alternative procedures or tasks. So there is a flexibility here. I would say that the most important aspect here is maybe the fact that to understand that this arbitrary order is actually modeled by mutual exclusion. And then we have this classical mutual exclusion of in this case, 1 resource and 2 tasks. And actually we have already discussed that here when I had a more complex situation. But this picture just illustrates how automata with tasks can be handled with a shared resource that either could serve this sequence or that sequence. And when you synchronize them together in the Petrinet, you get this picture. And then it's interesting that this place or this state here in R corresponds actually to this place, this dashed place, which is actually not necessary to add, because when you are in that state, you know that you are also in that state in this B1. And that state corresponds to, or let's say, no, it's this state. Yeah, here's a B1 and B1, then you are in this state and in that state in the other model. So when you synchronize automata and you represent that by Petrinets, you get typically some additional places that are not necessary to include. Because what happens when you include, when you execute B1 here is that you add one token there and one token there. And when C1 has happened, you take those tokens away. And of course, then you could just skip that and say that, okay, it's enough that I add one token to one place, and then you can go on later on. So you get some redundancy, you could say, in when you go from the automaton to the Petrinet description. But you see that classical examples of Petrinets are exactly these sequences of, you could say, flows of parts with some shared resources. And in this case, it's only one shared resource. In this example, I had two shared resources, and unfortunately also booked in opposite order, which generated the problem with deadlock. Here we only have one resource, but of course I could also have added a resource R2 and some additional behavior up here. But okay, if in the end it's quite common that we for calculation computational aspects would like to boil down to automata, especially if I should use these reduction methods, which I will talk about a little bit tomorrow. And in that case, you need in the end to go down to automata, and then it's good to know that a shared resource can always be described by this type of, in this case, a three-state model. Booked for the left or for the right side, or available or free is maybe a better word. Yeah, another thing which one could ask is, can we include some kind of memory in sequences? And for instance, here, if in the automaton A here, there is obviously two alternatives here, A1 and A2. But if we would like to have a specification saying that, okay, if I take the decision A1 here, I should also go for B1 here. And if I take an A2 here, I should also take A2 down here. That means that we need to memorize what happened up here, because the choice down here will be restricted to what was decided up here. So it's typically a memory function that needs to be added. And that means that for each choice here, for say the combination A1, B1, you introduce one additional automaton. First, say B1, including A1 and B1. And for A2, B2, you introduce then a capital B2 automaton with A2 followed by B2. Okay, how can we model this by a Petrinet? Well, we could say that this behavior A1 or A2 is represented up here in the A part of the Petrinet it has a choice here, either A1 or A2. And then these dashes here means that, okay, anything can happen in between here. But it's important that when the execution A1 happens, then you get a token down here, which means that it's now possible to execute B1. And in that case, it will not be possible to execute B2 because B2 requires one token up here, and that will not be available because that requires that you execute A2. But now A1 was executed, and then the token takes the left way, so to say, the left path. But instead, if we here have the freedom and A2 is executed, then B1 will be blocked while B2 is possible. And you see once again that these states in the automaton, the first and the last, they are dashed here because they are not required. It's actually only an automaton where you have A1 followed by B1. That is what we need, so to say, combine here. But to get a complete automaton, you must have also an initial state and a final state. But these are actually not necessary in the Petrinet. So then I have finished the presentation of Petrinets, and after a short break, I will continue then with how we can add variables. And adding these variables first to automata and then to Petrinets will give, so to say, my favorite own model, namely Petrinets with shared variables. So let's take a 5-minute break, but let's see if there are any questions.
Participants, if you have any questions. Thank you, Professor.
Okay.
Any questions you have?
Does not look like that. So then we take a short break.
Okay.
Jag kan höra när man kan ta ner lite grann på de här exercise eller tutorials eller något. Vi kallar det lite övningar då, men jag vet inte, alltså lecture and tutorial. Ja, det var stort tutorial.
Men det är väl att de ska sitta själva och träna lite och räkna kanske på det. Tänker på vad det blir eller
Ja, det kan det bli övningar då.
Ja.
Exercise session.
Och det har du inget här alltså.
Då igår hade jag plockat fram en massa gamla tentator som gick igenom.
So participants, many of you are asking for sharing access to the drive that I've shared with you. In fact, you are trying to access it from your other email ID, which is not registered with us. So please try accessing it using your own like registered email ID. You will be able to access that. Okay.
Okay, so maybe we can start again.
Yes, please.
Let's see. So now I will go on with extended finite automata, or let's say that generally extended automata models of different types, including also continuous time dynamics and timed system, but that's a very small part. I will come back more to that next week. But specifically, introducing variables to our model is a quite important procedure, and it has become more and more popular in the literature and in the research communities. So then we assume that we have not states but locations. And the reason why we not call it states anymore is that the state is first defined when you have also defined the value of the variables. So the location combined with the variables generate the states. And then the notion location has been there for quite a number of years. We still have the event label as before, but now we also have variables, and for simplicity now I just call them say v1, v2, v3, etc. And then to be able to perform a transition, you have not only the fact that you are in this location, you also must satisfy some guards on your variables. And you could also perform some actions on your variables. So a guard could be, for instance, v1 is equal 0 and v2 greater or equal to. If this is satisfied, if say v1 is equal 1 and v2 is equal 4, then you can perform this transition because the guard is satisfied. But if v2 is, for instance, only equal 1, then you have to wait until v2 is has been increased to 2. And at the same time, you could also update your variables. So for instance, if v1 is equal 0, the next value of this variable could then be v1 equal 1. And that could be then could be considered as an action. There are other ways to describe this. You could actually just write v1 equal or v1 prime equal 1, with prime meaning that it's the next value of v1 is equal 1. That is a notion I will use later on. But this guard and action is quite standard in the literature, so I start to present it in that way. So the total state is then the combination of the actual location and the value of the variables in that location. To illustrate this, we can start and go back to our tank process, which we had the first lesson. Then I illustrated that both by an automaton with only events or actions. If you are in a state in between, let's say, if you are in this initial state and if the you have an output flow here, so after some time the level goes below y0, then you open the pump or the valve. So you get more input, and then we expect that after some time you get to the level y1, and this event y1 high occurs, and then you close the valve, and then it repeats like this. And then we said that, okay, you could also represent this. Actually, in this case, we could say that in the states, you have u equal 0 and u equal 1 as two variables in these two locations now, if we should be careful. Then you could have y1 and y0 as variables, and actually they were from the beginning variables like sensor signals. If y0 is if the level is less than y0, then y0 is 0. And if it's above y0, then it goes up to 1. And in the same way for y1. So actually, the physical system has natural variables, and a PLC also includes variables here. So now I use that fact and say that, well, I have a guard here saying that when y0 is 0, then I assign the value u equal 1 as an action. And then that is the transition going from, then you can make, when this is satisfied, when y0 is 0, you can make a transition to the next state where you have u equal 1. And then to get u equal 1, you also introduce an action on that variable. And then corresponding to go back again. So you could actually say that these extended finite automata, where you combine variables with states or locations, is actually much closer to what is implemented in reality. And that I show you now by a typical PLC control implementation by there are actually, I think there are 4 different languages in the PLC standard. There was a PLC standard established like 20, 30 years ago. IEC 1131 or something, I think it's called. And the most advanced model, I would say, is this sequential function chart. And that could be described as follows. Here I have a first step, it's called. And this step is actually not only a square, it's a double square. That is the initial step. Then when y0 is equal 0, you go to the next step. And then we have an action here. This was the guard, y0 equal 0. And then you have the guard, the action, and that is u equal 1. And here I also add a prefix called n, and that stands for non-stored. And that means that this variable u is equal 1, that is only valid in this step. Then when you could also, just to explain why I have this prefix, you can also have a stored action, which means that if I say, for instance, had written s here, then it means, and u equal 1 here, then that is a set action, and then you could have a reset action later on. But those are details I don't care about here. Now, when y1 is equal 1, I take the next transition, and the next transition is to go to this state, and then u should be equal 0. Actually, this is not necessary, because since this is a non-stored operation or an action, it means that when you leave this step, the u variable will automatically go down to 0, which I have explicitly said here. So you could say I add a little bit more than necessary if you go for the full SFC standard, but this is just to illustrate more clearly what is happening with this u action variable. So u is the output from the SFC, and y0 and y1 are the input signals to this. So this way is a traditional way to implement control functions in industrial systems, like using PLCs. You can also use function blocks, and there is also something called ladder diagrams, if you have seen that, if you are very familiar with PLCs. That is an old technique to describe what is used in old traditional logical control systems. Now I will go back to the EFAs and illustrate how two EFAs also can be synchronized. You know, this synchronization is always important, because even if we introduce variables, we still need to handle also a number of such EFAs to get something useful. So I assume more or less always that I have a modular system with a number of either automata or extended finite automata. So when we have then transitions with shared events, the corresponding guards must be satisfied in both E1 and E2 to be able to make a synchronized transition. Observe that that is only when you have shared events. So if the expectation is that both E1 and E2 should make something together, a shared action, then that is only possible when the guard in the corresponding guard in E1 and also E2 are satisfied. But then we come to a small problem here, that if there should be a conflict between the actions, if say E1 should say that, okay, the variable, what did we say here? I had an action V1 is equal 1. Say that is the first EFA. And with the shared action, yeah, okay, here I have an example. U is equal 1 in E1. But I have an action U is equal 2 in E2. That means that the same variable I would like in E1 to be 1 and E2 be 2, that is obviously a conflict. So we must simply avoid conflicts to be able to execute this transition. And then, of course, one could have different interpretations here. And some of my colleagues suggested quite a number of years that, well, okay, we could still perform the action, but we don't update the variables and so on. But to me, that sounds a little bit strange. So I would say that if there is a conflict between the next value of the variables, I say that the transition is not admissible. It's not okay to make a transition then. So you cannot have conflict between the variables to make to perform a transition. You must avoid that. And okay, one way to change this is that you introduce a new variable in E2, because maybe they are, I mean, if you say that it would be equal 1 in E1 and equal 2 in E2, it probably is that, okay, you have different interpretations of this variable. So then it's natural to, it could be natural then to avoid the conflict to introduce a new variable, say V then, for the second EFA. So now I will actually show you two EFAs and two corresponding automata and also Petrinets. And first I have here the EFA 1. What does that have? Well, first I identify here, I write out the initial value of the variable in this model. You could say that it's not clear if that should be written explicitly, but of course you must always have initial values of your variables, and you could say that if nothing is said, you can expect that the value of the initial value of your variables is simply 0. But I write that out here explicitly. Then the first automaton or EFA, sorry, have an action C1 and also a corresponding update of the variable V1 from 0 to 1. That's the only thing that is happening in E1. And in E2, I have a corresponding action C2 and an update of the variable V2 from 0 to 1. The third EFA says that, okay, there is now two events A and B, and they should be given in this order, A followed by B. And then I have in the fourth EFA, I have an additional specification saying that to make the B event, it's also required that both V1 and V2 must be equal 1. And when that is true, the fourth EFA says that then V3, an additional variable, should also be updated from 0 to 1. Okay, so this is just a toy example trying to illustrate what can happen in a synchronization of these EFAs. And actually, to illustrate this by a Petrinet, once again makes it quite readable, because the corresponding Petrinet is as follows. This behavior, that, okay, here the token in the initial state could represent the variable V1 that goes here, V1 is 0, and here V1 is 1. And here V2 is 0, and here V2 is 1. And this could also then mean that you get by this behavior the sequence A followed by B, but also that I need variable V1 equal 1, V2 equal 1, and then I also update V3. That is required to perform the B event. So this is actually modeled down here. So first C1 and C2 and A, and after that you can execute B. So you could say that, well, the Petrinet actually only focuses on the events, the actions of this. First C1 and C2 in arbitrary order, and also the event A. First after that, you can make a B event. And in the EFA model, that condition has been modeled by these additional variables. Okay, we could also model this by corresponding automata. And in this case, you could say that then I introduce first one automaton representing the first variable V1 from 0 to 1. And I also introduce the shared B event here in all these cases. And for the second automaton, I have first V2 equals 0 and 1, and A3 is the same as the EFA, and A4 just focus on the third variable, V3. So you could say that the transformation of the EFA up here to automata as well as Petrinets is not totally trivial, but there are algorithmic procedures to do this. And when we first introduced these CFAs, we had some way of doing that, and it's actually not that complicated. But I will not present those algorithms to you. I refer to the literature on that. Now I will also go back to the buffer example again. It's a favorite example for me, especially when you look at the relation between different models. A buffer with, say, n elements. In that case, we can actually also introduce a variable representing the different states here. So when v is equal 0, it's the first initial state. V equal 1 means that one part is in the buffer, and up to v equal n, then there are n parts in the buffer. We know that this can also be described by a Petrinet, where you have n tokens in the, so to say, place representing the number of available places in the system. And from the beginning, there are n available places in the buffer. And when A happens, you move tokens up here. So, you know, when there are high numbers of tokens, we write it as a variable or as an integer instead of writing the tokens explicitly, because I mean, if n is 100, it's no meaning to write 100 dots here. It does not give anything. But then the question, can we also model this by an EFA? And of course, the answer is yes. Actually, EFAs quite often comes with this one location model. And sometimes they are also called the flower models, because you get a number of self loops, which could, I mean, if I write 4 self loops here, it could be considered maybe as a small flower. So when is the A event possible? The condition is that, okay, you must, the buffer cannot be full. So V, the variable V must be less than n. And if you perform this action, then V is updated such that the next value is V plus 1. So next value is current V plus 1. This action or this transition can go on from the initial state V is equal 0 and until V is equal n. Then it's not possible anymore. Then you must also activate this action. And to take away an element, V must be greater than 0. And then you reduce the variable with one step, with one. Yeah, the next value is simply V minus 1. So here you see 3 different models. The explicit buffer model, which is of course okay to write, but I mean, if you have 1,000 elements in the buffer, you can not at least write it out explicitly. But of course, you can write like this and then just write V equal 1,000 here. And it's okay. I mean, everyone understands what you mean. But if you combine that with other types of systems, it can be quite quite messy. The Petrinet is actually quite nice here. And I combining buffers with, for instance, machines and resources and so on, then definitely these Petrinet models are very, very good to describe that. The EFAs also works fine, but you have to look a bit detailed on all your variables up and down here, and sometimes it's a little bit of a mess to understand that too, but it's still possible. Definitely you reduce the graphical representation. And there are also some very efficient algorithms for this type of models. For instance, we have implemented verification and even synthesis for not only automata, but also for EFAs in our tool Supremica. And you can make both verification and synthesis for that. And also some of the abstractions I will talk about later can be applied on this type of model. A little bit more complicated, but it's possible. So now I will show you another illustration here of how you can work with these models with automata and variables. And then I use, in my view, quite nice notation. It's a little bit of sugar added to your this description here, but it makes things more readable, I would say. And quite often, or typically, these variables, the actions are that you reduce it by one step or add one increment one step. So then I simply write R minus when I mean R, the next value is R minus 1. And I write R plus when I mean that the next value is R plus 1. Now it's very critical when we work with this type of models that we also define the domain of our variables, because that completely defines what is possible. Or, okay, you could say that here I put actually additional guards here, which define the domain. But I mean, here I said, okay, V is equal, next V is equal V minus 1 is only possible if V is greater than 0. It means that we expect that V cannot be less than 0. V is limited below 0 and above equal n. So you could say that the domain of this variable is an integer from 0 to n. Now, if I introduce another rule, which is quite interesting, if I say that, well, the domain of my variable here is from 0 to n, and I say that, well, okay, if I try to make an action which goes outside the domain of the variable, then the action is not admissible. This means that in this case, I can skip actually this V greater than 0 if I have said that the domain is limited below to 0 and above to n, because then if V is already equal n, next V is equal n plus 1 is not possible because you go outside the domain, and next value equal V equal minus 1 is also not possible. So by these notations I'm introducing here on the next slide, this model could actually have been written as B/V minus, means to the reduction, and here A and V plus, and that's enough. And you see that that is quite useful and simplifies your description. So here, instead of writing R, I mean, explicitly when it's written here R minus, it said that, okay, next value is the current minus 1. It's R, next value equal R minus 1, but also that the current value of R must be greater than 0, because otherwise you cannot, if it's already 0, it cannot be -1. So this is these are valuable shortcuts, I would say. So in this case, I assume that I have one shared resource, and I call that R, and another resource or buffer maybe, which is called B, and the domain of these two variables R and B are from 0 to 2. So they can these variables can only take the value 0, 1, and 2. So this actually implicitly introduce the guards that R must be in the interval from 0 to 2, and also for B. In this case, I also assume that R is equal to and B is equal 0. Those are the initial values. And that could be considered as, well, okay, if I have a resource, typically in this literature, it's normal that when you require a resource, you change the value of, in the real-time system and concurrency theory, there is something called a thing that is reduced until it goes down to 0, and then you cannot do anything more. So this R could be considered as actually as a semaphore, and also in the Petrinet, you start here with two tokens, and then you can remove first one token and a second token, but when R is empty, when R is equal 0, then you cannot do anything more. So this fact that you start here with R equal 2 is the initial value of this place, you could also say. Let's see here first what this model says. Okay, the first model says that, okay, I would like to make an R minus and then B plus and then R plus. So that means that I require first a resource and then I leave it back. It's the same for G2. It also requires the resource and it leaves it back when I write R plus. And we can say that both G1 and G2 creates one element each. So B is increased from 0 to 1 here. And say if you after this execute G2, B is increased from 1 to 2. But of course, it could be the opposite order. I mean, here you have really concurrent systems. In which order all these things are executed, you have there is no restriction on that. Here in G3, there is a condition that, okay, when B is equal to, then you should use the resource R again. You should require R minus and then an R plus. So if we look at this from a Petrinet point of view, we can also model this. Now you could say that this resource R is very easy to model. It's a mutual exclusion, and that's very easily represented in a Petrinet. In this case, for instance, G1 require here a resource, and this R minus is simply that you take one token there and go on with the token here. And then you leave it back before you reach the final state here, or final place. This B plus is here modeled that in the second transition, you add one token to this place. So I should maybe have written also B here. this place represents the B situation or the B variable, while this place represents the R variable. So that was the behavior of the first system. It adds one token up here. And then you have more or less the similar behavior for the second system. It also adds in this second transition, it adds one token to this B place. Now, how can we model this B condition B is equal to? And then we have actually used for this weighting, because then I require two tokens here in the B place to be able to execute the first transition in G3. But I immediately give it back to that place. The tokens. I take two and give it back immediately when this first transition is executed. Then after that, there is also an R minus and R plus related to this transition. So first an R minus, meaning that I take one token from this R place, chof, I need that here. And then one token is removed from this R place. And then in the third transition, I give that token back to R. Now you have already seen that things, even in the Petrinet, start to be a bit messy. Not talking about what it should be if we represent this as a full automaton. Because what this model now shows is the explicit states in these three systems, G1, G2, G3. They have states. I call them, say that Q1 is equal 0, 1, 2, 3. Q2 is equal 0, 1, 2, 3. And Q3 is equal also 0, 1, 2, or 3. And then I had the variables R and B. So to generate the explicit state, I have then, you could say, the location variables for the three EFAs. I could then, okay, I've called them L1, L2, and L3 to follow up on that. Also, here we have the two variables R and B, and there we can note that the initial value is that the EFAs, they are in their initial locations 0, 0, 0, and then the initial value of the variable R was equal 2, while B is equal 0. And then the different rules that are included here up, the conditions for these variables, that they are reduced. And you also have this condition, for instance, B equal 2 for G3. We can just see here that, okay, if you make this transition, then the first model has used the resource. It is reduced from 2 to 1, and the first EFA is going from state 0 to state 1. And then you play around on this, and in the end, all states are in their third. All EFAs are in the third location, and the variable R is still 2. But the buffer B has also been increased to 2. So this is the final, which can also be considered as the marked, the desired state. And here we can see just by looking at this that it seems to work fine. There is no deadlock state. There is a flow here, and in the end you reach this. This is something that of course this is more or less the limit of what you can do on paper. But of course it's easy to perform this in a computer. But still, okay, well, what is this? Is it about 16? About 30 states, I guess. For more complex systems, you soon will come up to very large system, and then, of course, you can represent this in different ways. And one way is to use these so-called BDDs, binary decision diagrams. It's a way to represent large systems by Boolean variables. Another way is to use these SAT solvers, by which you can say you also have Boolean variables, but then it's more not in terms of a tree structure or data structure. It's just the basic variables you formulate in the propositional logic, but there are solvers for evaluating these logic expressions, which means that you can have a huge number of variables and it still works fine. But then there are also abstraction and reduction principles, which I will mention more about later here. Well, I think that we stop there. Because now what I will continue on a little bit the afternoon before I give some more examples is how you can also introduce first representing all things by variables, and then in the end also introduce, instead of, this is a complex Petrinet, which is quite similar to the one I had in the former example, but that can also be described by these types of flows, where I also here introduce variables. And this is my, we can say, favorite example, Petrinet with shared variables. That's Lennartson's model. Okay. Let's stop there, and if you have any questions, yes, you have.
Thank you, Professor. Any questions, participants?
Okay, there was a good question here. How can variable value inconsistency? Okay.
Sorry,
how can variable value inconsistencies be handled when both a guard and an action are taken? I don't know when you wrote this question. Handle inconsistencies when both a guard and an action are taken. I mean, actually, a guard is not taken. A guard is a condition that must be satisfied to be able to perform an action. But let's say that maybe I should use the word event here because now we talk about actions as updates of variables. And then you could say that, well, I mean, a guard is either true or false. And if it's true, then you can perform, then the transition is admissible. So there are no inconsistencies there. Either it's satisfied or not. And I mean, of course, it could be that you have a situation where your guard will never be satisfied. And of course, then maybe either you have modeled things in a bad way, or this is the fact that your system has that property. But there is still a problem with these actions if they are inconsistent. If one action tries to and you synchronize, if one action wants you to update to 2 and the other update to 1, then you get problems. I'm not sure if this was an answer to your question, but if not, you can add more comments.
Sir, I I wanted to mean that if an action is taken before the guard is satisfied. So,
is somebody speaking? Anyone?
Yes, yes.
yes. Hello.
Deepojwal, you have to speak a little aloud. Deepojwal.
I was asking if action.
Can you increase your loudspeaker or volume? Sorry, yeah.
Hello.
Yeah,
Yeah.
yeah.
Yeah, I was telling if an action is taken before a guard is satisfied. So suppose an action is taken and changes the value, which previously the guard was not being satisfied, but because of the action, the guard now satisfies. So will that transition be taken, or how to handle?
No. I mean, if the guard is not satisfied, the action cannot be taken. That's simply the fact. Yeah. So this is a strong concept. But okay, actually, at the same time, you have a point there, because if the event is uncontrollable, and maybe that was what you were thinking about, then that is an event that is taken by the plant, and that can be taken by the plant independently of the fact that the supervisor has, in the supervisor you have now added a guard, and there could definitely be a conflict. So the uncontrollability problem generates this type of, if you call it, inconsistencies. So once again, you must in that case also guarantee that the supervisor does not try to restrict the plant in a way that it tries to restrict uncontrollable events, because that is not allowed. And in that way, you could say that this is a synthesis question. I mean, you have to either verify that this is not the case, or you simply have to avoid that situation. So you have to you cannot allow those kind of transitions where the plant tries to can make an uncontrollable event, and that is not accepted by the supervisor.
Thank you, sir.
Yeah, good question.
Yeah.
Very good question.
Any other questions? And please put on your video so that we can take a snapshot, all of you. Thank you. Thank you all. Thank you, Hirajyoti. Thank you, Shubhangi, Vinay, everybody. Thank you, ma'am.
Nice to see you all.
Yeah, it's nice to see all the participants.
Yes.
Very nice to see. Thank
now
you.
I start to remember some of your faces.
Yeah. So connecting with the participants or students makes, I think, the speaker feel so motivated, and that's important in any classroom interaction. It's important. Thank you. Yeah.
I just said to my wife, because she is not working on Friday, so she is also at home now, and I said, yeah, you get a bit tired after 1 hour of this continuous talking, and especially not if you just talk to a screen.
To a screen. Yeah, thank you. Shubhangi and Samir, I think you have already taken, or you're taking. Please do take snapshots, and thank you so much, all of you. We will be meeting at 6:30 p.m. Indian Standard Time, and I request you all to please be present before that time. Professor's time will be 2 p.m. perhaps.
Yeah.
So till then,
could I, Aparajita, could I just discuss with you a little bit about the program after this now?
Sure. So may I request, you can leave the session, and we will be meeting at 6:30 p.m. IST. Thank you all the participants.